Yeah, so just tell us next when you want the next slide. So go ahead. Thank you.
Okay. And how many minutes do I have for presentation?
A total of 30 minutes, so a few minutes for questions.
Okay, thank you. So good morning, actually good evening probably. This is Yuichi Tsuda from JAXA Sagamihara. So I'm sorry for not attending in person there. So I'm presenting from Japan about the current latest status of Hayabusa 2. So could you go to the next slide? Yes, so this is the overview of the Hayabusa 2 mission. So Hayabusa 2 is the second Japanese sample return mission to the small body, and it was launched 2014, and now already at the target asteroid Ryugu, which is a C-type asteroid, and we will return back to the Earth in 2020. So there are four key technical key points for the Hayabusa 2 mission. The first one is it is a round-trip mission, so it's a sample return mission using the ion engine for forward and return cruise. And we will do the in-situ science at Ryugu for 1.5 years using 4 landers and 4 remote science instruments. And the highlight is the touchdown and sample collection, which is now is planned in next month in February, and we have the spacecraft has a capability of doing 3 touchdowns and sample collection, and the final one is artificial crater forming. For that, the spacecraft is equipped with a kinetic impact device called a small carrier impactor, and if it is successful, we expect to create a 2-meter class crater on the surface of the asteroid. And if situation allows, we want to collect the sample in the vicinity of that crater to get the subsurface material. So could you go to the next slide? So on June 27th and last year, we successfully arrived at the Ryugu. So this is the photo taken right at on that day, on June 27th. So since then, we are working on the Ryugu almost like 24 hours, 7 days to take care of the spacecraft and also to observe and do the science activity on Ryugu. So next slide, please. And this is how the Ryugu looks like, as you may already know. So it's very surprisingly it's a top shape, and the size is 1 kilometer diameter across equatorial, and the horizontal vertical it's 900 meter. And if looked from the top, it looks almost perfectly the circular shape. And as you see, there are many rocks and craters all over the surface, and that actually making a lot of headache for us for doing the mission. So next slide, please. And here are some initial scientific findings of Ryugu. So as I said, it's a top shape and the very circular equatorial bulge, and the mean radius is about 450 meters. And we already determined the GM or gravity constant. It's a 30, so 30. And the rotation axis is about almost perpendicular to the orbital plane, but it's a retrograde. And the rotation period is, as we expected, it's a 7.6 hours. And it's a very dark asteroid with only 0.02 the reflectance factor, so it's very, very black. And there are a lot of craters and boulders, and it's twice as dense as that of the boulder density of the Itokawa. And we already observed some clue for the water, and that is to be submitted. That is now being submitted to some science papers. And also we observed the thermal or temperature map of the surface. Could you go to the next slide? And recently we are approved to have a name, terrain names on the Ryugu. There are already 13 official names approved by IAU, which includes some the ridge and crater and also boulder. So we already have a name to call the surface. So next slide, please. And the right after the arrival in the end of June, we started the extensive observation around about the Ryugu, and only 2.5 months later, we hold the landing site selection meeting in Sagamihara, which is held in August 17th. Which is participated by 109 participants from Japanese and European and American colleagues. And in that one-day meeting, we decided the landing sites for spacecraft and also 3 rovers, each of which are consistent with each other, not interfering with each other, and scientifically to get the maximum science outcome. And it was personally very surprising and exciting that we could decide it very smoothly on these 3 landing sites. And this is thanks to the 2 years of the preparations and the rehearsal using the training model of the Ryugu. So it was only one-day meeting, but actually we had a lot of preparation beforehand, and thanks to that, this big international activity was successful. And next slide, please. Yeah, so I just show here the conclusion of the landing site selection, and skip all the intermediate process. So finally, we decided we derived the one touchdown site for the spacecraft, and one site for Minerva landing site, and one site for Mascot landing site, and all of them are plotted in the map in the lower figure. So the Hayabusa spacecraft is to land to the equatorial region, designated as L07, L07 or 8, and M04. So we have 3 candidates, 1 primary, 2 backups. And the Minerva 21 rovers was to land on the northern hemisphere, designated as N6. And Mascot lander, which is the German and Kunes developed lander, and it was to land to the southern hemisphere, designated as NA9. Next slide, please. And based on this landing site selection meeting, decision of the landing site selection meeting, The first thing we did is the Minerva 2-1 operation, which was conducted in September 20 through 21st. So the spacecraft basically hovered at 20 kilometers in the nominal operation, but for this operation, spacecraft descent down to about 50 meters, very low altitude, to the targeted position, targeted location, and then deploy the 2 rovers at once, Minerva 2-1A and 2-1B, to the northern hemisphere landing target. And next slide, please. And it was very successful. And the 2 rovers were separated on the September 21st, and right after the separation, a few minutes later, it landed successfully to the surface of the Ryugu, and immediately after that, the 2 rovers start hopping and collecting data and constantly send back the data to the spacecraft. And the picture shown in this slide is one of the first picture we got from the Minerva 2-1 rovers. And because we confirmed all the first activity of the 2 rovers, we can say that it is the world's first mobile robot successfully performed on the surface of the small body. Next slide, please. And here are some pictures taken from 2 rovers. You can see very dynamic pictures. Even seeing the mother spacecraft itself, although it's not focused perfectly. And we can see that because the rover is hopping, it can even see the Ryugu from above the surface. Next slide, please. And also, could you go back again to what? Could you go back one slide? Yes, this one. So, and we can also obtain the scientifically variable data from Minerva 2-1 rovers, and from this picture we could first recognize that the surface is very bumpy and very even in the microscopic scale. So the pictures here I'm showing it is only a few centimeter to 10 centimeter scale. So you can see that the surface is covered by rocks rather than sands. And could you go back? Could you go to the next slide? Yes. So and this is the movie taken by Rover 1B, and you can feel as if you are standing on the surface of Ryugu for one whole day. Next slide, please. Yes, so this is a summary of the Minerva rover results. So 2 rovers were successfully operated, and the first one, 1A rover, was active for about 1 month, which corresponds to 113 sols, because the rotation period of the asteroid is 7.6 hours, so 1 month corresponds to 113. And even after that, we could observe a weak carrier signal continuously transmitting from the rover. So we are expecting that we can do more operation on these rovers. And the second rover, 1B rover, was active for about 3 days, which corresponds to 10 sols. And also this, also from this 1B rover, we can still observe as we carry a signal, indicating that it's still alive. Next slide, please. The next operation we did is the Mascot landing operation. The Mascot is developed by our DLR and Kunes partners, and it's the largest lander equipped on the spacecraft, which is 10 kilograms. And the operation itself is almost as similar as we did in the Minerva 2-1, but the big difference is because this lander is driven only by primary battery, so it can last for only 17 hours. So we have to concentrate on this operation and to keep the good communication link to the lander. Right after the separation, the spacecraft tried to keep the low altitude, 3-kilometer altitude, for 24 hours. And it was successful. We'll go to the next slide, please. Yes, so this is the operation summary of the Mascot lander. And the Mascot lander itself was operated from the DLR Operation Center in Karen and also from Kunes. And they control the Mascot via Sagamihara Operation Center, and also we used JAXA Deep Space Center and also NASA Deep Space Network and ESA extract stations. And all the commands and telemetry goes to the Hayabusa spacecraft as a communication relay node. And the first day, Sol 1, the Mascot was separated successfully, and a few minutes later, it successfully landed and settled on the ground. That's in the upside down orientation, which was favorable condition for the Mascot. And so the DLR operation team decided to do a big hop on the second fall. So they commanded to the Mascot to do the big hop. And after that, they confirmed that Mascot orientation was in appropriate position. So it was successfully done. And after that, they started the extensive observation, a whole asteroid day. And so 3, they retrieved all the scientific data observed through the Mascot, and they decided to do additional hop to do the additional science. And it was also successful, and the final data was downlinked right before the third night for the Mascot, and they confirmed that 17 hours of successful operation on the surface. So next slide, please. Yes, so this is some of the pictures taken by the Mascot, and they sent this kind of very high resolution microscopic surface images of the Mascot and of the Ryugu. And the Mascot is equipped with four science instruments, so and they retrieve much valuable data, not only the image data. Next slide, please. So I want to talk about the landing of the spacecraft. So before that, what I want to mention here is that we tried the 4 low altitude descent so far. And low altitude means less than 100 meter axis. And the latitude range of plus minus 30 degrees has been proved to be accessible with higher than expected guidance accuracy. And based on that, we are now trying to finalize the actual landing operation to be conducted in February. Next slide, please. So this is the actual result we have obtained for the low altitude descent of the Hayabusa 2. So 4 of them, the best accuracy was about 3 meters to the landing target, to the low altitude target, and at worst it was 30 meters. But by assessing these operations, we are now thinking that the landing accuracy itself is about 15 meters. And the original design before launch was the landing site was, we think it is 50 meters. So the 15 meters is higher than what we actually planned. So based on that, we are now finalizing the operation procedure of the touchdown. Next slide, please. But the problem is the surface of the video is severe than we are expecting. And this picture is the landing site selected in the landing site selection process. And within that, we only found a 20-meter safe area instead of 100-meter safe area. So the original performance of the Hayabusa 2 performance of 50-meter landing accuracy is not enough. And even the 15-meter landing accuracy is not enough because the radius is only 10 meters. So we have to do something to accommodate with this very severe terrain. So could you go to the next slide? Yes. So this is a summary of what I'm explaining. The original design assumes a touchdown accuracy of 50 meters, but what we found is the only 10 meter or less than 10 meter safe area of the 08 area. So in last October, the project decided to deploy the target marker first instead of the spacecraft landing to precisely evaluate the terrain relative navigation guidance accuracy, and which was successful. And now the project is in the final phase of assessing the landing zone safety and also adjusting the landing procedure to it. Next slide, please. Next slide, please. Could you go to the next slide? Is there a problem?
The main feed line has disconnected.
Yes, I can hear you.
Yes, the main feed line. This is the operator. The main feed line has disconnected.
Yes, please. Could you dial in again?
I'm sorry, I have to wait for them to dial in. I don't have a number for them. This is. Hello, can you hear? Can you hear me? Should I dial in again?
Hi, I'm going to be the next speaker. I think if we just wait, hopefully they'll reconnect us soon.
They're dialing in now, sir. There's some feedback. Do you have multiple lines connected, sir? Because there's feedback coming from your line.
Yes. Yes.
One moment.
Okay.
They're almost through. This is the operator. Main feed line, you are open.
All right.
Okay.
All right.
Can you hear? Can you hear me?
Yes. Okay. So we got cut off. You were on the slide towards spacecraft's touchdown. Can you pick up there?
Okay. Yes.
Slide 20. Yeah.
So can I continue?
シュルさん、this is Abel さん。So ちょっと待ってください。So slide 21お願いします。
Okay, so I already finished this page, so could you go to the next slide, please? Okay, I will speed up. So this is the touchdown sequence, and what we actually did in the October 25th is instead of the spacecraft touchdown, we dropped the target marker as a visual marker, and then terminate the descent and the ascent again. And after the target marker release, the spacecraft tries to hover above the target marker and tries to autonomously track that target marker. And by doing so, we confirmed that the spacecraft could autonomously track the target marker and hover precisely right above the target marker. And we observe that we see how precise we can do for that. And could you go to the next slide? And this is the result. So the red circle is the original target area, L088B, which is a 20-meter diameter area. And the target marker was dropped right at the edge of that circle, so 15.4 meters off from the center of the landing site. And so based on that, we are now evaluating that the landing accuracy is 15 meters. But what was nice about this is that we could track this target marker very successfully. So could you go to the next slide? Yes, so this is the actual movie we got from from that operation. So the bright spot in the center is a target marker, and so you can see that the spacecraft could place the target marker always on the center of the images, and that this is the evidence that the spacecraft could hover at 20-meter altitude for a long time. The red box corresponds to plus minus 1 meter box. So this means that we could hover. If we successfully find the target marker, then we could hover with the plus minus 1 meter precision. And based on that, we are now building the landing operation procedure. Next slide, please. Okay, so this is another movie we got from that operation just after the target marker separation. So the spacecraft is ascending to the home position, and you can see the beautiful scenery of Ryugu from the side camera. Next slide, please. Yes. So, based on that, that operation, according to that operation, we now more precisely know where the safety region is, and we find out two regions in the vicinity of the target marker. One is the red region called L08B1, and the another is the green region called L08E1. And we are now still choosing which one is safer for the spacecraft landing, and we will decide it in the early February, and then try the first touchdown in the week of February 18th. Next slide, please. So this is the final slide. So in the last year, for 6 months, we successfully did the rover landing and Mascot lander landing operations, and we did 2 touchdown rehearsal operations. And based on that, in this year, we will try the first touchdown, and then the crater forming will follow. And if situation allows, then we will try the touchdown around the crater. And we still have another Minerva 2 rovers equipped aboard the spacecraft, and we will release it in the second half of this year. And we'll leave the Rover in the end of this year and return to the Earth in 2020. So next slide, please. I think this is the last one. So thank you very much.
Thank you. Do we have questions? I'll repeat it.
How fast is the land-use special surface, and what would the spacecraft able to see the land-use after the landing?
The question is, how fast did the rovers or the landers touch the surface, and was the spacecraft able to see them after they touched the surface?
Yes, the two Minerva 2 and Rover, Mascot rover, both of them are landed at about 10 centimeters per second velocity, and before and after the landing, the spacecraft could observe the landing trajectory as a bright spot. So actually we got some images before and after the bouncing of the 2 rovers, and we are now still analyzing that and retrieve the landing trajectory.
Thank you. Other questions? Thank you very much.
Thank you very much.